Hi everyone, welcome back to another video. This video is going to be on equilibrium. So let's start with the first question. Which substance below is the strongest electrolyte and which is the weakest? So when we're deciding which electrolyte is strong and weak, it depends on two things. First, it's the degree of ionization, essentially meaning is it 1 plus, 2 plus, 3 plus, or the same for the minus version. And the second thing is the number of ions. So basically just the coefficient that we see in front of the ion. So let's go through all four of them. So we have KBr first. This will dissociate into K plus and Br minus. Now we have HNO2, which will dissociate into H plus and NO2 minus. Then we have H2O. This is a covalently bonded chemical, so this is actually a non-electrolyte. And lastly, we have Na3PO4. And this will make Na plus ion and a PO4 3 minus. And then we have to balance this equation by adding a 3 in front of the Na plus. So these are all the equations balanced, and now we just look at the two requirements of an electrolyte. So we see that with KBr, we have 1 degree for both of them, and we have a coefficient of 1. So there's 2 ions, and that goes the same for HNO2. H2O, as we said, is a non-electrolyte, so we know this is going to be the weakest. And then when we look at the last one, we have a coefficient of 3 and 1 PO4 3 minus ion, so this has 4 ions in total. And it also has the highest degree of ionization with a plus and then also a 3 minus. So that means this is going to be the strongest electrolyte. And then the final answer will be B. Next, when 1 mole of each compound below is added to 1 liter of water, which produces the strongest electrolyte solution. So this is similar to what we did above, except we also have to make sure that each of these are soluble in water. So let's go ahead. So CaCl2 makes calcium ion and 2 chloride ions. And then what we need to use now is the solubility guidelines on our formula sheet. And let's see if it's soluble. So this will be soluble because I see it in rule number 4, and it says that chlorides are soluble except group 2 fluorides, which are insoluble. So this means this is soluble because of rule 4, and now we can move on. So AgCl, let's see if it's soluble or not. This, in fact, is not soluble because it says in rule 3 that salts of silver are insoluble. So this is insoluble, and this is not going to be our strongest electrolyte. Next, phosphoric acid. This is a weak acid, so it only partially ionizes. So if you see into the lecture slides, it says that weak acids or bases are not going to be strong electrolytes. And then let's look at the last one. Methanol is a covalent molecule, so it's not really going to dissociate into constituent ions. So this means that the strongest electrolyte is going to be the one that's soluble and the one that will dissociate into ions. Next, which acid below is the weakest? So they've given us all of these different acids and also the Ka value, the coefficient of ionization. So first we have to understand where this Ka value comes from. So this is the standard equation that we use. And then the equation is the concentration of the products over the concentration of the reactant. So when we talk about which acid is the strongest, it basically means which one will dissociate into ions the most. So a stronger acid leads to more dissociation, which basically means more products. So we have a higher concentration of H plus and also the conjugate base. So this means that a higher Ka value, because these two are on the numerator, right? So it'll make a higher Ka value, and this higher Ka value therefore means that it's a stronger acid. And the one that has the lowest Ka value, because we're looking for the weakest, is going to be A. Okay, question 4. Determine the total ionic equation for the reaction that occurs when aqueous solutions of barium chloride and sodium sulfate are mixed. So first thing we do is we write out the two reactants. So we have barium chloride, which are aqueous solutions, and we have sodium sulfate. Now let's just do our double displacement. So we will have barium sulfate and sodium chloride. And let's balance the equation by adding a 2 in front of the sodium chloride. So I haven't written the states yet because we need to see first which ones are soluble. So let's look at barium sulfate. Barium sulfate is not soluble because if you look at rule 6, it says sulfates are soluble except those of calcium, strontium, and barium. So barium sulfate is insoluble. So I'm going to put S because it makes a solid. And then NaCl. This is going to be soluble because of rule 1, salts of group 1 cations are soluble. So this will be aqueous. And then to make the total ionic equation, basically all we have to do is separate all of the aqueous species into their constituent ions. So for this one, it will be Ba2 plus, Cl minus, but we have 2 of them, so I'm going to put a 2 in front. And then we have 2 Na plus, SO4 2 minus. And then on the other side, we keep all of the solid and liquid species and we only separate the aqueous ones. So this one is still going to be barium sulfate solid and 2 Na plus 2 Cl minus. And that is our total ionic equation, and this one matches option B. Next, which of the following pairs of aqueous solutions will not produce a precipitate when mixed? So just like before, let's do our double displacement. So this will be AgCl plus NaNO3. And then we have to look at the solubility rules to see which one will and won't produce a precipitate. And a precipitate will form when it's insoluble. So let's see. AgCl, rule 3 says that salts of silver are insoluble. So AgCl is insoluble, so it will be a solid and form a precipitate. Let's look at the next one. Do the double displacement again, and we'll get barium sulfate plus NaCl. And we actually had this just above, and we saw that it was rule 6 that made it insoluble. Next, we have NH4NO3 plus KCl. And let's see if NH4NO3 is soluble. This is soluble because rule 1, it says the NH4 plus cation is soluble, and also says that nitrates are soluble, so rule 1 and 2. So we have something aqueous here, and then KCl is also going to be soluble because K is a group 1 cation, and because of rule 1, we know that that makes it soluble. And for good measure, let's just see what the last one is. So this will be PbI2 plus KNO3. And because of rule 3, we have lead, and lead is insoluble, so PbI is insoluble. So the one that will not produce a precipitate is the one that doesn't have a solid, and that will be option C. Next, question 6 for the reaction. What is the value of K for the reaction below at the same temperature? So we have our original reaction, and it's been changed up a little bit to form this. So I'm noticing two things that are happening. The first one is that the equation has flipped. And the second thing is that the coefficients have doubled. So we have to figure out what the new K value is based off of the information that we have in the original KSP value. So once again, let's write out how we derive K. So this is the equation. So reactants and then the products. The lowercase in front of the uppercase just represents the coefficient, and the uppercase represents the species. So K is the products to the power of the coefficient over the reactants. Yeah, so this is how we get our value. So when we flip the equation, it means that C and D are going to be on the left side and A and B are on the right side. So what that does is we have to flip this equation too. So basically we take the reciprocal of the original K value. So I'm going to write the new K value here. It was originally 7.1 times 10 to the power of negative 9, so I'm going to do 1 over 7.1 times 10 to the negative 9. So we've accounted for the flipped equation now. What about the doubled coefficients? Well, when we double the coefficients, it means that we'll put a 2 in front of here. And then these coefficients will make it to the power. So basically we're squaring everything. So how do we account for doubling the coefficients? We can just square this whole entire thing. And then this will give us the correct new K value, which will be 1.98 times 10 to the 16, which is approximately just 2.0 times 10 to the 16, which is option C. Next, question 7, consider the reaction. K equals 850 at 350 Kelvin. What is the value of K for the reverse reaction at the same temperature? And what does this tell you about the reverse equilibrium mixture? So similar to what we had before, we have the K of the forward, which is 850, and we need to figure out K of the backward reaction. And as we learned a few moments ago, we just take the reciprocal, which will give 1.18 times 10 to the -3. So it's either B or C. And then what does this tell us about the reverse equilibrium mixture? We have to compare what it's like compared to the forward reaction. So K of the forward is greater than K of the backward reaction. And the forward is B over A, and the backward is A over B, because it's products over reactants. So if this value is greater than this value, then that means there is more B than A. So there is mostly B. Okay. For the next few questions, these are Le Chatelier principles reactions. So we're going to use this one equation for all of them. And we're going to look at some different scenarios and predict how the equilibrium is going to shift. So first, the partial pressure of NO is increased. If we increase the partial pressure, remember that the equilibrium will always shift to counteract the change. So because we increase the amount of NO, it's going to want to decrease that to balance it out, and then the equilibrium will shift towards the products. So the first one is B. Next, some NO2 is removed from the reaction mixture. So this will decrease. So if we remove some NO2, the equilibrium is going to want to shift so that we make up for the NO2 that is removed. So it's going to make more NO2 by shifting towards the products. So it's B again. Next, the reaction mixture is transferred to a vessel with twice the volume. So with these volume questions, you want to look at which side has more moles of gases. So we have a coefficient of 2, 1, and 2. So overall, on the reactant side, I have 3 moles of gases, and on this side, I have 2. So if there's twice the volume, it's going to shift to make up for that extra pressure change, and it's going to shift in the direction where there's more gases, which is the reactants. So it will shift towards A. On number 11, the temperature of the system is decreased. So when we look at temperature, we want to look at this value right here. So this is an exothermic reaction because we have a negative in front of here. So the forward reaction is exothermic. So if we decrease the temperature of a system, it's going to shift in the exothermic direction, which is the forward direction, so it will shift towards the products. And then if we have an increase in temperature, it's going to shift towards the endothermic side. So always remember, decreased temperature, exothermic, increased temperature, endothermic. And then finally, we have helium gas is added to the rigid container at a constant volume to increase the total pressure. So helium gas is not part of the equation, and it only increases the total pressure. Whenever there's a pressure change, it will only shift the reaction if it changes the partial pressure. So only partial pressure matters. And then when we have an inert gas like helium being added, it's not going to change anything. So this is C, no change. Only partial pressure matters. Okay, moving on. For the reaction, Kp equals 280 at 1000 Kelvin. A 10-liter reaction vessel at 1000 Kelvin initially contained 0.5 moles of SO2, 0.3 moles of O2, and 0.2 moles of SO3. calculate Q and determine the direction of the reaction, how it will shift to reach equilibrium. So what we need to do to calculate Q is basically Q is the same thing as K, but K is at equilibrium and Q is what is currently going on. So it's like the current state of the reaction. So what we need to do is, it's the same equation. So our Q equation is going to be the pressure of the product, SO3 squared, because we have a coefficient of 2, and this will be over the reactants. So P of SO2 squared plus P of O2. That's the equation we're going to use to calculate it. So all we need to do now is use the information we have to calculate what the pressure is going to be for each of them. So the pressure, remember the equation PV equals nRT? We can rearrange it so that it is nRT over V. So for SO2, it's going to be 0.5 moles. And then the R value, which is 0.083 on your formula sheet, is a constant. And then the temperature in Kelvin, which is 1000, over the volume, which is 10 liters. So the pressure of this will be 4.15 bars. And then we repeat the same thing for the other two gases. So for SO3, we have 0.2 moles, and then the same thing for the rest of the variables. And this will give 1.66 bars. And then lastly for O2, it is 0.3 moles. And this will be 2.49 bars. Okay, so we've calculated the pressure for each of the gases, and now all we have to do is plug in to the equation. So Q is 1.66 squared over, sorry, this should be multiplied, over 4.15 squared times 2.49, and we will get 0.064. So we can eliminate these two, but does it shift towards the products or does it shift toward the reactants? How we figure this out is we compare it to the K value. So it tells us that for the reaction K is 280, and this is much smaller than that. So this means if the Q value is too small, it means the numerator is too small, and the numerator has the products. So that means there is not enough products. So it's going to shift towards the products. So always remember that if Q is smaller than K, it will shift towards the products. And if it's the other way, it shifts towards the reactants. So this is A. Next, for the reaction, a mixture at 35 degrees Celsius contains these concentrations. In which direction will the reaction shift to reach equilibrium? So this is kind of the same thing as we did above. So remember that for gases, we can use either concentration or pressures, and then for aqueous solutions, we can just use concentrations. So they've already told us the concentrations for each of the gases, so we can just plug that into our equation. So remember that Q is products over reactants, so it's going to be concentration of NO squared. Don't forget that the coefficient has to go in the exponent, times the concentration of Cl2 over concentration of NaCl squared. And now we just plug. So this is 0.02 squared times 0.008 over 0.5 squared. And we get 1.28 times 10 to the negative 5, or 1.3 times 10 to the negative 5. And then which way does it shift? We compare it to K. So this is slightly less than K. So this means that it's smaller than K, so it doesn't have enough products. So this means that it will shift to products again. So the answer is B. Okay, question 15. For the reaction, a flask initially contained only COCl2 gas at a partial pressure of 5 bars. What is the equilibrium partial pressure of CO? So this is a little bit different because we know the K, but we need to know what the partial pressure is. So we know that the equation is COCl2. I'm going to start by making an ice table so we can track how the reaction proceeds. So we have initial change in equilibrium. So initially we have 5 bars of COCl2, and it contains only this, so we have 0 amount of the other 2 products. And the change is going to be minus x plus x plus x. And then equilibrium is 5 minus x, x, and x. So what we do now is we know the K value is 2.2 times 10 to the negative 10. And then this will be x squared. Remember, it's reactants over products. And this x squared comes from the pressure, the equilibrium pressure of Cl and the equilibrium pressure of Cl2. And they're both x, and so we just make it x squared. And then underneath we have 5 minus x. And then all we have to do is solve for x now. So we could just calculate it like this, but we can also use the small x approximation to try to make our calculation a bit easier. So how do we know x is small? It's if k multiplied by 100 is less than the initial pressure, which is 5 in this case. So k times 100 is 2.2 times 10 to the negative 8, and this is still much smaller than 5. So therefore, we can confirm that x is small. And what this allows us to do is just get rid of this minus x, because we're assuming that x is so small that it doesn't really matter if 5 is subtracted by x because it won't change our value very much. So now we can calculate this much easier, and we can get 3.32 times 10 to the negative 5. And what does this x mean? That x is equal to the partial pressure of CO, which is what we're looking for. So the answer is B. Question 16, what is the molar solubility of CaF2 in a 0.2 molar NaF solution? So what is molar solubility? It's when you have a solid that dissociates into ions. So whenever you see an equation like this, where you have a solid and then 2 aqueous or like however many aqueous species on the product side, you're probably going to be calculating for molar solubility. And basically what it is X. So let's set up our ice table. So we have a 0.2 molar NaF solution, and this NaF solution dissociates into Na plus and F minus. So basically, the 0.2 molars will dissociate into F minus ions, and then this is the initial amount of F minus concentration that we have. And then the calcium is just 0. So then it's plus X and then plus 2X. And then the equilibrium will be X and 0.2 plus 2X. And all we have to do now to find molar solubility is to solve for X. So 3.9 times 10 to the minus 11 equals X times 0.2 plus 2X to the power of 2 because of the coefficient here. And then when we solve for X, we can do a small X approximation once again, and that allows us to ignore this part. So this will be 0.04x, and then solve for x, we get 9.75 times 10 to the negative 10. So the answer is B. And then I'll write a note here that molar solubility is just equal to x when a solid dissociates into ions. And then we don't have anything on the denominator because we can't have a concentration or a pressure of a solid. So we ignore that and then we just do the two products that are multiplied by each other. Okay, question 17, second last one. So a 25 milliliter sample of 0.004 molar PbNO3 is mixed with 25 mils of 0.004 molar NaCl. Determine QSP and indicate whether a precipitate should form. So I like to write out the formula so I can see it clearly. So once again, how do we calculate QSP? This is same as above. We have a solid that is dissociating into ions. So QSP is going to be the concentration of Pb2 plus and Cl minus squared. So all we need to do now is calculate what the concentrations of these two ions are. So after mixing, the total volume, because we have a 25 milliliter here and a 25 milliliter here. So overall, it's going to be 50 milliliters. And the reason why we do this is because we can calculate the concentration by using the formula C1 times V1 equals C2 times V2. So for the concentration of Pb2 plus, it will be C2, or sorry, this is C2. So then it will be C1 over V1 over the new volume. So initially the concentration was 0.004 and the initial volume was 25 milliliters. And then over the new volume, which is 50 milliliters. And when we do this, it will give us the new concentration. which is 2 times 10 to the negative 3. So that's the new concentration for Pb2+. And because we had the same numbers for NaCl, this is also going to be the concentration for Cl-. And now we can plug this value into our formula. And QSP will be 2 times 10 to the negative 3 times 2 times 10 to the negative 3 squared. And then we will get 8 times 10 to the negative 9. So we cross out C and D. And does a precipitate form or not? So we compare it to the KSP value. So this is smaller than the KSP value. And when it's smaller, it means there is less products than there is at equilibrium. And because there's not enough products right now, it is going to shift in this direction towards the products, which have aqueous species, and then the solid or the precipitate is on the left. So not enough products, shift right, and it shifts in the direction so that no precipitate forms and more aqueous ions form. So therefore, no precipitate. So then precipitate cannot form, and the correct answer is option B. Hopefully that made sense. Final question. A pharmaceutical compound has a measured log K of octanol being 5.2 based on this value alone. What is most likely true about how this drug behaves in the body? So we need to understand what K of octanol is. So basically what this measures is lipophilicity. And when we have a high K of octanol, it means that it is highly lipophilic. And basically what this means is it's going to bind to the fatty tissue and proteins in the body. Because philic, remember, it means liking. So if it's lipophilic, it likes lipids. So that's why it binds to fatty tissue and proteins. And it also states in the lecture slides that when the log of K-octanol is above 4, this indicates a highly lipophilic compound, and it has slow metabolism in the body. And our value is 5.2, which is above 4. So it will have slow metabolism or elimination in the body. So that means A is incorrect. And this means that it's highly lipophilic, so it will bind to proteins or fatty tissue. And this does provide us information about elimination. So that was the last question. Thank you for watching, and good luck studying.